All right, then. We're going to flip in here to going back to what we were talking about at the end of Friday's lecture. And in Friday's lecture, we started to explore the 4 different types of chemical reactions. We looked in particular at the synthesis reaction, which is the reaction where little compounds, little elements come together to make one product. And we looked at its opposite, which is the decomposition reaction, where one big compound splits off into tiny little molecules or elements as a result. Now, these next 2 are often presented together because they are so very much alike. They are the replacement reactions. And in the replacement reactions, we are talking specifically about single replacement reactions and double replacement reactions. Now, in single replacement reactions, what we are looking at are basically 2 things. We are seeing that we have an elemental component, which is depicted here as A, and a compound component, which is listed here as CD. Now, what happens in these is that the element will kick out a similarly charged element in the compound, and we get a new element, C, and a new compound, AD. And so what element gets kicked out depends upon what element is trying to replace it. If I have something that normally forms a negative charge, it's going to replace the other negative charge. If I have something that's normally positive charge, it's going to replace the thing that is positively charged. So in this case, A would be represented by a metal, which is zinc. And CD is represented by the compound copper 2 chloride. And so we can see in this case, it is the zinc metal that is going to replace the copper metal and give us copper metal solid and zinc chloride as the other product. And so why did the zinc replace the copper instead of the chlorine? Because the zinc and the copper both have similar kinds of properties. They're both metals. They both form positive charges. That's the driving force here. But the really tough thing about single replacement reactions is that it's not as simple as this looks. Sometimes when we put an element and a compound together, we actually don't see any reaction at all. And that is because of something called the activity series. Now, the activity series gives a ranking of one element and its reactivity relative to other elements and their reactivities. And so the higher up on the list that we are, the more reactive that element is. And so every element that is high can replace any of the elements that are below it. So to answer these questions, will magnesium replace hydrogen? Well, we got to look. Magnesium is here. Hydrogen is here. Magnesium is higher than hydrogen on the list. So the answer is yes. Magnesium will replace the hydrogen because magnesium is higher on the activity series than hydrogen is. Will aluminum replace hydrogen? Well, again, we got to look at where aluminum is. I can see that aluminum is right here below magnesium. And so yes, it too is higher than hydrogen. It is going to replace the hydrogen. But will aluminum replace magnesium? No, it won't, because magnesium is higher on the list than aluminum is. Will iron replace zinc? Well, let's take a look at the list again. I have iron right here, and I've got zinc right here. Zinc is higher than iron, so the answer there is no. So single replacement reactions only occur if the element that is doing the replacing is more reactive than the element that is already in the compound. If the two are different from each other in that regard, then a reaction won't actually happen. So if I look at iron, and compare it to barium, barium will react and replace iron. Barium will not be replaced by iron. It's a one-way street. If it happens in one direction, it will not happen in the other direction. So that's an interesting kind of dimension to single replacement reactions. They don't always happen. They don't always happen the way that it's written on the page. You have to evaluate them in terms of the activity series. And so when they happen, the reactions look like this. Magnesium, in this case, will kick out the hydrogen to make magnesium chloride and hydrogen gas. The aluminum would displace the hydrogen similarly, but the iron would not. So some common examples of this. I can look here. This is a reaction called the thermite reaction. And you see it is very, very exothermic. Thermite reaction is used in a number of different cases. It's used in some steel refining cases. It's also used in like the railroad industry as a way to do track repairs, where you can make a small batch of molten iron in this reaction, drop the molten iron into a crack in the railroad track, and it'll repair it and smooth it out so that you can use it again. Copper oxide. So the Statue of Liberty here, that green patina that is on the Statue of Liberty is a compound that is an oxidation compound of the copper that is in the bronze that was made out of that Statue of Liberty is made out of. Using iron, you can actually strip some of that copper oxide off, get it to the copper shine that it was before. In the case of the Statue of Liberty, though, it's kind of a lost cause. The sea environment around Ellis Island makes a really excellent conductor, and makes it really difficult for the copper oxide to be prevented from forming. So when it was originally shipped here from France, it was not green. It was actually bronze colored. But over the period of a couple of years, that green patina started to form on it, and it's basically been that way ever since. Now, the question that you have to ask yourself in these is, what's happening to the charge on the metal that is doing the displacing? So if I look at the aluminum here, the aluminum went from uncharged metal to a +3 charge in the aluminum oxide. And in a contrasting nature, the iron went from a +3 state to no charge as a product. The iron in this reaction had no charge initially. It now has a +2 charge. The copper here had a +2 charge. It now goes to a 0 charge. This is known as a broad class of reactions known as redox reactions. And basically, we can look at them as any kind of reaction where the charges on the elements will change. It gets a lot more involved than this, but this is kind of a good starting place for us to look. And so in single replacement reactions in particular, we see high evidence of that redox character, where we see that the charges are definitely changing. The metal that is inserting itself is getting more positive. The metal that is getting kicked out is becoming more negative. So that's single replacement reactions. Double replacement reactions are very similar. One of the reasons why they carry the same name, replacement. What's happening there is that like charges are replacing each other. So in this case, the C and the E are going to switch places. C was with D, now it's with F. E was with F, now it is with D. And so if I look at this from a real world kind of example, the C would be copper. And we see that the copper went from being with the chloride to being with the sulfur. And the sodium went from being with the sulfur to being with the chloride. So double replacement reactions and single replacement reactions are very similar in that regard. What we're talking about are two ions or two elements switching places. The difference between single replacement and double replacement are the number of compounds involved. In single replacement, we have one compound being involved, and the other thing that is involved is an element. In double replacement reactions, we have two compounds being involved. And so the term single replacement or double replacement is a reference to how many compounds are involved in the reaction itself. So in double replacement, we have two compounds that are changing parts. In single replacement, we only have the one compound that is changing parts. Now, another key feature of double replacement reactions in particular is notice your phase of matter here. Aqueous, aqueous. Most of our double replacement reactions occur in aqueous solution. That is, the substances that are being reacted are dissolved in water first. And the other kind of side result of that is that we usually get one of three things to occur in the product side to let us know that a reaction took place. And the one of the things that recur is we either get a solid formation, as is the case in this one. We call that precipitation. We can also get gas formation, or we can get neutralization, which usually comes with a heat transfer as well. So in the case of neutralization reactions, I have an acid and a base together in a reacting vessel. They neutralize each other. The acid and base basically wipe each other out. From a visual standpoint, unless I have an indicator present in the solution, you're not going to be able to tell that anything actually occurred. But if you monitor the temperature of the reaction, or you do something simple like just touch the reaction vessel to your skin after you've neutralized it, what you'll find is that the temperature increases. Neutralization reactions are exothermic. They generate a good bit of heat. And so you can feel that, or you can measure that. And so, as I said, the way that we can tell that a neutralizate or that any kind of double replacement reaction is actually occurring is it's going to fall into one of these three subcategories. We're either going to find a solid form, a precipitation. We're going to have a gas formation, so we're going to see bubbling. Or we're going to have a neutralization reaction where we get as a result of the neutralization, water and a salt, and the salt compound, the ionic compound, is usually dissolved in water. As I mentioned, these reactions, the neutralization reactions, are difficult to pinpoint just by visual cues, unless we are using an indicator that shows a change in pH, or we are monitoring in some kind of way the temperature of that solution. We'll notice that the temperature will increase as the neutralization reaction proceeds. In precipitation reactions, we see an insoluble solid form. That insoluble solid is known as a precipitate. We can indicate the nature of that by indicating that a solid has formed that is not dissolved. And that sets it apart from the stuff that is still aqueous and dissolved in water. So to answer this question, what is the white solid here? Well, sodium chloride would stay dissolved in water. This has to be the barium sulfate that is left over. How do we go about identifying that precipitate? How do we go about identifying whether a precipitate is formed? This is where we reference something called a solubility table. Solubility tables give us some ideas about how to predict solubility, how to determine whether or not something is going to be soluble or insoluble. And we can pretty much break this down into 3 categories. First category I'm going to highlight here in green. These are compounds that are always soluble. So if I have a compound that has an alkali metal in it, sodium, potassium, rubidium, cesium, or the ammonium ion, those will always dissolve in water. If I have a nitrate or an acetate, those will always dissolve in water as well. The second one I'm going to highlight here in yellow. These are the groups right here. These are what we would call usually soluble. So sulfates, chlorides, bromides, iodides, these are usually soluble in water. There are some exceptions to them though. For sulfates, we're talking primarily about lead and mercury, silver, but also some of your alkaline earth metals, calcium, barium, strontium. For your chlorides, again, for the most part, soluble. The ones that you have to watch out for, silver, mercury, lead. If you have silver, mercury, or lead with any of the halides, it's going to be insoluble in water. Otherwise, we should expect it to dissolve. The last group here, we're going to highlight in red. These are rarely soluble. Silver compounds are rarely soluble. Oxides and hydroxides are rarely soluble. Chromates, carbonates, phosphates, sulfites, silates. These are rarely soluble. Now, there are exceptions to those as well. The exceptions primarily come from these first 2 groups. So think of this list as kind of a top-down hierarchy. If it's in the top group, the higher up it is, the more reliable, the fewer exceptions there are. So if I have sodium with sulfide, it doesn't matter that sulfide is rarely soluble. Sodium being always soluble trumps that. Sodium's solubility is more resonant, more important than sulfide's usual insolubility. And so what we can do is we can kind of put these together and see, okay, I've got this ion with this ion. What group do they fall into? Do they fall into the green group? Then we know it's going to be soluble. We're going to put AQ in those parentheses. Is it in the yellow group? Well, let's evaluate. Is it one of the exceptions in the yellow group? If it is, solid. If it's not, aqueous. And if it's in the red group, then chances are really good we're going to put an S next to it because it's a solid, it's not soluble. So if we determine something is soluble, we write it in as AQ. If it is insoluble, then we write it in as a solid. And so as far as phases of matter are concerned, that's how we dictate, that's how we tell the difference between the two. All right, any questions about that? Now, one piece of particularly good news is you are not going to be alone in the evaluation. You will be given a solubility table like this in pretty much every circumstance where you might have to identify a precipitate. So if I tell you this and this come together, you should have access to a solubility table like this to tell you, okay, that's soluble, or no, that's insoluble. So bookmark this somewhere, table 5.4 in your textbook. When it comes to evaluating double replacement reactions, this is an invaluable kind of source. So let's take a look at this practice problem. First thing it wants us to do, balance the equation. Then circle the precipitate and underline the product that stays dissolved. So here's the reaction itself. Some of you did this reaction in lab, especially if you're with Mr. Miller. Those of you that are in the other classes, we didn't do it because this particular compound is toxic and really, really hard to get out of your glassware. So setup for this, I've got, okay, first of all, I should recognize I've got nitrate present on both sides of the reaction. Anytime I see a cluster of atoms like that, I know from a balancing standpoint, I want to keep them together. So I'm going to evaluate lead. I'm going to evaluate nitrate. I'm going to evaluate potassium. I'm going to evaluate iodine. I'm going to do that on both sides of this equation. And I can see that I have one lead, I have two nitrates because of this subscript of 2 on the outside. I've got one potassium and I've got one iodine. On the other side, I have one lead, one nitrate, one potassium, and 2 iodine. Now, from a balancing standpoint, I need to recognize that I've got I've got issues on both sides of the equation. So I'm going to have to do a little bit of balancing to get it right. Now, I can tackle either one in whatever order I want. Since nitrate's out of balance on this side, let's take care of that first. So I put a 2 in front of the potassium nitrate on this side. That means my nitrates go to 2. My potassiums also go to 2. And as I highlighted on Friday, this is usually what happens in replacement reactions when I go to balance them. I end up in a scenario where I've got 2 different elements out of balance by the same amount, and they happen to be in the same compound on the other side. So a 2 here takes care of the potassium, takes care of the iodide, and now we're all balanced out. So I've got my balanced chemical equation now. The second part, circle the product that precipitates, underline the product that stays dissolved. Okay, for this, I'm going to have to go back to my solubility rules. Now, my solubility rules tell me that potassium compounds are always soluble. So my potassium nitrate here, I got potassium, which is always soluble. I also have nitrate, which is always soluble. Potassium nitrate is going to be soluble in water, so I'm going to underline that one. Now, by process of elimination, we can determine that the lead iodide, the lead 2 iodide, is the yellow compound here. Let's see if we can't do a little bit better than that. Let's look at the sheet. Chlorides, bromides, iodides. We can see that iodides are usually soluble. Exceptions are silver, mercury, and lead. Well, lead is one of the ones that we are looking at. We're looking at lead 2 iodide. This would be one of those exceptions. So this must be our insoluble product. This is the one that is precipitate. Any questions about this example? All right, then let's move on to another. Got another practice problem here. We're mixing solutions of cadmium 2 nitrate and sodium sulfide. We need to balance the equation to identify the precipitate. So, from a standpoint of balancing, I should be able to recognize that, again, I've got nitrate as a cluster on both sides. So I've got cadmium, nitrate, sodium, and sulfur on both sides. And if I follow through in my counting, I have 1 cadmium and 1 cadmium. I have 2 nitrates, but only 1 on this side. I have 2 sodiums, but only 1 on this side. I have 1 sulfur and 1 sulfur on this side. The only ones that are out of balance are the sodium and the nitrate. They're both on the same side of the equation, so I just need to put that coefficient there to turn those both into 2's. Now, as far as identifying the precipitate is concerned, again, we go back to our solubility rules. Our solubility rules tell us that sulfides are usually insoluble. The only times that they are not is if they're with an alkali metal or an alkaline earth metal. Cadmium is neither. Cadmium is a transition metal. The precipitate then has to be the cadmium sulfide. Now, I could also look at it by process of elimination. Sodium compounds and nitrate compounds both are in the always soluble list. So this one was going to be, sodium nitrate was going to be soluble in water regardless. Our solubility table also tells us that the cadmium sulfide should precipitate, which it does. All right, this problem is in a very similar kind of setup. I can see that I've got chromates on each side. I've got everything balanced other than I have 2 chlorides here and 2 sodiums here. So very similar to the last problem, the balance is going to be that way. Identifying the precipitate here, well, sodium and chlorine. Sodium chloride is soluble in water. Anyone that's ever dissolved salt in water knows that one quite well. The answer here is going to be barium carbonate, or excuse me, barium chromate, which again we could verify on our table here. Most chromates are soluble. The exceptions include your alkali metals, magnesium, calcium, aluminum, and nickel. And barium is not on that list of exceptions. So my precipitate is the barium chromate. All right, any questions with these ones? All right, so let's move off of precipitation and move into gas formation. Gas formation comes as a result of certain types of reactions when they combine, those reactants combine to form gases as the double replacement reaction product. So where we see this often are things like carbonates, sulfides, and other compounds like those when they react with acids. So this is very common among acids reacting with somewhat basic solid compounds in particular. So calcium carbonate, for example, when it reacts with hydrochloric acid, the double replacement reaction that we would anticipate would have the calcium and the hydrogen switching places. Calcium goes with the chloride to make calcium chloride. We look on our solubility chart. Chlorides are usually soluble. There are a few exceptions, lead, mercury, and silver. Calcium is not one of those. It dissolves in water. The other product that we would anticipate is hydrogen carbonate, H2CO3, sometimes known as carbonic acid. Well, the thing with carbonic acid is carbonic acid doesn't actually exist as H2CO3. It exists in the sense that when carbon dioxide is bubbled into water, carbonic acid is created as a byproduct, a literal synthesis between the carbon dioxide and the water. That compound, however, is not terribly stable. And so when it's formed as the product of a reaction, what we see is a very quick and spontaneous decomposition of that carbonic acid into the water and the carbon dioxide. And that is what creates those bubbles. These are the same bubbles that we experience when we open a can of soda or seltzer. These are the same sensations that happen when we take an antacid. The acid in your stomach reacts with the calcium carbonate in the antacid, and it usually creates a little bit of it neutralizes the acid first, but you also tend to get the side effects of you feel a little bit of gas in your chest or in your stomach that you have to let out. And that's a result of the carbon dioxide byproduct. You get a similar kind of reaction with baking soda and vinegar, because baking soda is sodium bicarbonate, NaHCO3. And so it reacts with acid in the same kind of way in vinegar to make carbonic acid, which decomposes into the carbon dioxide and water. So that kind of reaction response out of carbonates is very, very common. In neutralization reactions, what we see in those cases is a true acid, and we can identify a true acid based upon its compound starting with H, and a true base, a compound that ends in OH, coming together to make water. Water, H2O, we can think of as the H combining with the OH. So I've got H2 and O that way. That's the product of the double replacement reaction. The other byproduct coming from the sodium and the chloride, being left over, this is our ionic compound, our salt. So the real key with these ones in particular is that these can be monitored with temperature, because these ones also generate heat. So if I do an acid-base reaction in a vessel and I put a thermometer in it, what I'll notice is that the reaction will cause the temperature inside of the vessel to rise. And that is an indicator that a reaction is actually occurring, because otherwise it's really difficult to see. Hydrochloric acid, clear and colorless. Sodium hydroxide solution, clear and colorless. Sodium chloride solution as the product, clear and colorless. So if I combine those together and just looking at it that way, it's very difficult to see that anything's actually happened. But if I do it with temperature monitoring, I can see that the temperature does go up, and that it helps us indicate that the reaction has actually proceeded, that we have a reaction that did occur. So let's look at this practice problem here. What is the balanced chemical equation for the reaction between calcium hydroxide and sulfuric acid to make water and calcium sulfate? So we've got calcium hydroxide, CaOH, taken twice, reacting with sulfuric acid, H2SO4, and the product of the reaction is water, H2O, and calcium sulfate, CaSO4. Now, if I'm evaluating this, all I'm asked to do is balance it. I can see that I have no common ions on either side other than the sulfates. And so I'm going to take that into my consideration. Calcium, oxygen, hydrogen, sulfate are going to be the things I look at. Now, in other types of double replacement reactions, You usually are able to pick out more ions than those, but because the hydrogen and the hydroxide turn into water, it's not going to be as easy to see that way. So on the flip side, calcium, oxygen, hydrogen, sulfate. I have 1 calcium, 1 sulfate, 2 oxygens, and 4 hydrogens in total. So I've got 2 in the hydroxides and 2 in this acid. On this side, I have 1 calcium, 1 sulfate, 1 oxygen, and 2 hydrogens. This is a double replacement reaction where, again, we can see oxygen and hydrogen are both out of balance. They're both out of balance by the same degree. Now, it's not quite as easy as some of the other ones we've done where it's been, 2's over on the left side and 1's on the right-hand side. But we can see if we look at it closely, I have half as much oxygen as I need on the product side, half as much hydrogen as I need on the product side. The number I'm looking for here is a 2. I'll make this a 2, and 2 times 2 here would give me 4 to balance that out. This kind of word equation is actually the subject of your last proficiency in this class. Proficiency number 5 requires you to do this kind of thing, combining your nomenclature knowledge, where we give you chemical names, and you have to turn them into chemical formulas and then balance the equations. So one of the reasons why that particular proficiency has been hidden from you for so long is because until you pass nomenclature and equation balancing, it's pretty much impossible for you to do well on that particular proficiency. So that one will remain hidden until either we get near the due date lines, it'll open up naturally, or you pass nomenclature and equation balancing on your own, and then in that case, it'll unlock early for you. You can go ahead and take it at that point. But until that point, it's going to remain closed until the week before the first due date, or you pass those 2 individually. All right. Last question that we'll work on today before we call it an afternoon. Balance this equation and then determine, is the product soluble in water? So the equation is this. We've got the reaction in your stomach between your gastric juice, your hydrochloric acid in your stomach, and milk of magnesia, which contains magnesium hydroxide. Products of that reaction are water, since it's a neutralization, and magnesium chloride. Now to balance this, very similar kind of process to what we saw in the previous example. I've got hydrogen, chlorine, magnesium, and oxygen on both sides. For the hydrogens, I've got 1 here and 2 more here, a total of 3. In the chlorine, I have just the 1. In the magnesium, I have just the 1. In oxygen, I have the 2. On this side, I have 2 hydrogens, 2 chlorines, 1 magnesium, 1 oxygen. So I've got a lot of things out of balance here. I'll start by balancing the thing that's the easiest to do, and that's the chlorines. 2 HCl's will give me the 2 chlorines I need to balance out the chlorine. It'll also give me 4 hydrogens now, 2 in the acid, 2 in the base. And now we can see we're in the same scenario that we were before. Double the hydrogen, double the oxygen on the reactant side. So I need to double the water on the product side. Is this product soluble in water, magnesium chloride? Well, for that, I need to go back to my solubility chart. Nothing really in there about magnesium, but chlorides are featured particularly in the usually soluble category. The only exceptions are silver, mercury, and lead. Magnesium is none of those. So we can answer in the affirmative. Yes, this is going to be aqueous. So that's where we'll stop for today. There's just a little bit more to clean up, which we'll get to on Wednesday. A couple more practice problems to look at, and just some general identification, trying to help us get through the identification part of this. You should be able to do post-lecture 5.4 just fine, however. We'll just kind of clean up the loose ends a little bit on Wednesday before we move into chapter 6 and start talking just a little bit about calculations regarding chemical equations. Have a good afternoon.